Hello, my name's Michael Avery. I work for Cadence Design Systems. I'm going to spend a few minutes talking about the VHDL, Rem and mod operators. People often confuse these thinking they're the same thing, and they try and equate the use of mod as it's implemented in VHDL to the mod or modulus they find in other languages and wonder why it doesn't behave as per their expectations. So what we'll do is go through this and give a few examples, and hopefully after that you'll be able to not only understand this but actually work out in your head what the result is. So VHDL has these operators Rem and mod. They're built into the language. So the examples of how you use them are shown here. We can see that B Rem C gives some result that we can assign to some other value, like A for example. If you're looking for how these are described in the language reference manual, these are actually called multiplying operators, and that's not just a peculiarity of VHDL, it's true for any other languages. Division, Rem and mod are all called multiplying operators, even though you're actually dividing things. Being as they specify a divisor, if you're using them in VHDL, they're only synthesizable if one of the operands you're using is a power of 2. So basically it's not going to try and calculate something for you if you're not using a power of 2. Rem and mod have different names, so clearly they can't do the same thing, although they do under certain circumstances, and we'll discuss what they are. The LRM gives a description of what mod is and what the result will be, although all it supplies is a formula which can be satisfied. It doesn't actually explain why. So if we were to look in the LRM, for example, here, we notice one thing. This is the 2008 LRM. Multiplying operators, these are the ones here, mod and rem, that we're talking about. And it goes on in this paragraph down here to show you what the relationship is between rem, mod, and how we can work this out. But it still doesn't tell us, why does mod exist then? We could probably have a good guess of what rem will do. It will give us a remainder. But how do we know what that means? So the Rem operator is easy to understand. It gives a remainder for a simple integer division. So here we're showing the plus sign just for it's known as an identity operator, as you may know in multiple languages. So saying plus 5 is saying the same thing as 5 times plus 1. So we're just showing it here to make it completely clear which sign we're talking about. So here's some results from the Rem operator with some randomly chosen operands. So we're using all combinations of sign, i.e. plus or minus 5 and 3. And the result of Rem is simple to understand. It's just a division and a remainder. So if we have plus 5 divided by 3, we can divide 3 into 5 once and leaves us a remainder of 2. So that would be the result of that operation. And we can see here the other results as well. So already can we see what patterns emerge here? We can see that for Rem, that the result always follows the sign of the operand to the left of the Rem. So here plus 5 yields plus 2, and the opposite for minus 5 and minus 5. So that's clear to understand. So the mod operator is not so easy to understand. If you've seen a VHDL operator using mod before, it's a very high probability that it's in some cookbook example of resetting a count at a certain value. So for example here we're assigning to count the value of count incremented mod 16. So remember what mod will do, it will divide by 16 and it will leave us some, we won't call it remainder, but it will leave some bits left over. So what this actually does, and why you see it in cookbooks, is because it describes a counter that counts from 0 to 15 and then resets to 0 again, continually. So mod in, not just in VHDL but other programming languages is often used to do that, perform some operation every X number of iterations. So what this means is that 16 is actually a synonym for 0, as is 32, 48, 64, and any multiple of 16. As this is a power of 2, we might expect that our synthesis tool would synthesize this statement here. But this still doesn't really help us understand what mod is or what it does. So before we actually go into detail on that, what we'll first talk about is precedence. So mod and rem are operators which are deemed to have equal precedence. Now if you put a plus or minus in front of a number, this has a lower precedence than the mod or rem. So if you do something like we saw earlier, minus 5 rem plus 3, it's the same as saying minus and then putting in brackets and therefore forcing precedence 5 rem plus 3. So in some circumstances we use this, we might have to be careful on what other operators are there to know, what are we actually saying. So in the simple case, like we've shown in an example, it doesn't really affect what we see, and we'll actually demonstrate that with a tool running example in a moment. So if we want to understand mod, one way of doing it is visualize it as being a clock. So if you were to look at a clock on the wall and it happened to be 1 o'clock and somebody said to you, what time will it be in 15 hours time, you would come to the conclusion 4 o'clock very quickly. And although you might not have known it, in your head you've worked out modulo 12, because every time the clock goes around 12 hours, it's as if we reset to 0 again and start counting. So if we advance 15 hours into the future, we advance 1 full rotation plus another 3 hours. Now the difference with the mod operator, and first thing to say about this is the mod operator and VHDL behaves in a way prescribed by the VHDL, but there is no common convention across languages or even in mathematics what modulus and modulo mean. They can be talking about two completely separate areas of maths. So they don't do the same thing. So if you're looking in, for example, C++, and again we'll run an example of that, you may wonder why I use the, in C++ I use the percent sign, which is I look in the, IEC standard and see that that's telling me it's a modulus operator. Why don't we get the same result as we do in VHDL with the same operands? What we're talking about here is the VHDL mod operator. So a rule of thumb is that the sign of rem follows the sign of the first operand, that's to the left hand side of the operator. The sign of mod follows the second operator. Okay, so this is just a rule of thumb, it doesn't explain what mod does. So to do that, we'll go back to our analog of a clock. So what we've got again is a combination of operands using both signs plus or minus, and the operands we've chosen are 5 and 3, not for any particular reason. We could have chosen anything we liked. The way in which we can work out the mod operator in our head quickly is that if we're given an expression A mod B, imagine a clock that has digits from 0 to 1 less in magnitude than B. And the sign of the numbers on that dial is determined by whatever sign B is. So in this case, being as we've got plus 5 mod plus 3, our clock will have the digits 0 to plus 2, because 2 is 1 less than 3 and the sign of this second operand is positive. What we then do is we start counting around our clock for a number of steps determined by our operand here A. Okay, and the direction we go in, and this is why it differs from rem, depends upon what the sign of AB is. So if the sign of A multiplied by B is positive, then we go clockwise. If the sign of A times B is negative, then we go counterclockwise. So for this one here, we'll go clockwise. We're going to count for 5 steps, starting from 0, on this dial that we've manufactured earlier. Okay, so we go from here, we go 1, 2, 3, 4, 5. Therefore, the result is plus 2. The sign of A multiplied by B is going to be negative because we're multiplying plus 5 minus 3. So we're going to go anti-clockwise on this clock that we manufactured. And the digits on this clock will have a minus sign in front of them because this second operand has got a minus sign in front of it. So we're going to be going counterclockwise from 0 for 5 steps. So we go 1, 2, 3, 4, 5. Our result is minus 1. Okay, so it's different, not only different in sign, but different in magnitude. Again, we've got this one here. We're going to go counterclockwise because the product of A and B is going to be negative. And on the dial we have, the numbers are going to be plus because this second operand is plus. So we're going to start from here, going counterclockwise, and we're going to obviously end up with the result. We're going to go 1, 2, 3, 4, 5. So it might have been obvious to us there before we started. We'll have the same magnitude, but a different sign for the result. And for -5 mod -3, the numbers on the dial are going to have a minus sign in front of them because the second operand does. And the product of A times B is going to be positive, therefore we'll go clockwise. So from 0 we count 1, 2, 3, 4, 5. Okay, so that's how you can do it in your head. So this gives us a way of, in the sense of being pragmatic here. This gives us a way of just doing things like the counter that we saw previously, resetting when we get to a certain number, and gives us this concept of having two directions of rotation as well. So we can use this to implement whatever we choose. So here we've got another set of operations just to prove it wasn't a complete fluke that it worked last time. Let's do it for this as well. And the more examples we go through, of course, we might be able to see certain patterns and certain conditions we can predict quite easily in our heads. So the numbers on the dial are going to be from 0 through to 1 in magnitude less than 4. Okay, so we're always using the numbers 7 and 4 in here. It's just the sign that changes. So the numbers on the dial will be 1 in less in magnitude than 4, which will be 3. The numbers on the dial depend upon what the sign of this is. So in this case it will be plus 0 to +3. And what we do is from 0 we're going clockwise because the product of A and B is going to be positive. So from 0 we go 1, 2, 3, 4, 5, 6, 7, the result +3. Let's go, we won't go through every example, we'll go through this one. Okay, so the numbers on the dial are going to be positive again. We're going to go counterclockwise because the product of -7 and 4 is a negative number. So counterclockwise. So we go counterclockwise for 7 steps from there on this dial that has numbers from 0 to 1 less in magnitude than +4. And the sign will be positive because the sign of this is positive. So from here we're going to go counterclockwise for 1, 2, 3, 4, 5, 6, 7 steps. Our result is +1. Okay, so what you can do is try it yourself. So if you wish, now will be a good time to pause the video. See if you can come up with some conclusions yourself if you wish. I'm going to continue and read the answer out in 5 minutes, so pause the video now if you don't wish to see the answer right away. Here's the answers, and again, just to prove it's not a fluke, this same kind of algorithm that we followed here, this same kind of thing we follow, works all the time. So it doesn't take much to work that out in your head. Okay, so why should you believe what I've said? Well, let's show an example of this actually running in a tool. So what we've got here, this is the code that we use to implement this. There's 2 files, notice here. There's one with this name here. It uses whatever the default precedence is for it. So in an expression like this, we're relying upon whatever the precedence is in the language. We're not forcing it with parentheses. And you notice the difference between this file and the others, and we've highlighted in tkdiff the difference here, is that in one of the files we're not using parentheses to force any kind of precedence. In this file here we are using it. So we're putting brackets around these operands to force the precedence. So remember the slide we talked about on precedence. And what we're doing is we're writing out 2 things in each of these files. So they're identical apart from the lines you see highlighted. And you can see that it's just a case of one line being commented out in one file while it's not in the other. And what we're doing is writing to the standard out what the dividend, divisor and quotient was the result that we get. And we're doing it for 2 things. We're doing it for the mod operator and we're doing it for the Rem operator. So what this will allow us to do if we go and look in this log file will be to see, well, we can get several bits of information from this. We can see, does the behavior of mod differ from Rem? And the answer we should already know is yes, it does. And another question that might concern us is, does putting parentheses around these operands affect the result I get? Because remember, the default precedence in the language, for the slide we had there, it doesn't yield a different result in simple cases like this, but it may do depending on how complex an expression you have. So we've run these simulations here, and the log, so you notice in this pane up here, the logs represents the ones with precedence forced and without precedence forced. So let's go to an example. The last example we did, it was all combinations of 8 being the left-hand operand of mod and 5 being the right hand operand, and we had a variety of cases. So one of the cases was, let's get this up here to prove that what we're saying is what the results of a simulator would be. Okay, so we've got here +5. Sorry, we'll have to go minus. We're starting with minus here. So -8 mod -5. Okay, so look at the mod. -8 mod -5 is -3 is the result. That's correct. And -8 mod +5, -8 mod +5, the answer's +2. Okay, and we need to go all the way down the file, see the other one. So we should hopefully be confident that we've tried it on 3 different sets of operands now and it's worked all the time. So here we've got +8 mod +5, so +8 mod +5 is the answer's +3, and +8 mod -5, and the answer's -2. Okay, so you can see here that the mod rem represents the same operands but different operators, and we can see the results different with the same operand, so we know it behaves differently. So the special cases which help us to identify and quickly evaluate when we see some code containing mod is that if you have something like this where we've got a mod and +1 or a mod -1, the result will be 0 for both of them. For any A, the following will be a runtime error. So remember, we're dividing with mod, as we are with rem, as we are with the normal division operator. So if you try and divide by 0 and you don't trap it in your code, then you've only yourself to blame when you get a runtime error. If B is non-zero, so if we have a mod B and B is non-zero, then for any value of B, the result of the following is 0. So if we have 0 mod and anything else, the result is 0. As long as the operand B is not 0, of course, because that would give us our divide by 0 error. If A and B have the same magnitude, then the result is always 0. If A and B have the same sign, then A mod B has exactly the same result as a rem B. Okay, so mod and rem behave the same if A and B have the same sign. Okay, meaning that we have -A and -B, or we have +A and +B. And this gives confusion. This is why in other languages like C++, for example, if you use the % operator, which if you read the in c++.com or anywhere else you find it, it calls it the modulus operator. It doesn't behave the same as the VHDL one. It behaves like the Rem operator. Okay, so if we're going to look on some C++ code now. This is the C++ code that we're going to execute, and you notice in here what we're doing is we're using this % operator. So the % operator in C++ is what's called the modulus operator, not to be confused with the mod VHDL operator. This is the whole point of this, to try and show you they're not the same thing. This behaves like a remainder does. So what we're doing here is we're assigning to my quotient the result from that with 2 different operands. Those operands are taken in via the cin. So basically it's just an interactive console. And we're writing out that. We're also writing out the value of this fmod. So basically this is a modulus. This is a function inside of the math.h library. You can go and search on this on c++.com or somewhere like this. It will tell you what it does here. Floating point remainder with rounding. And so if we wish in this is not the intention of this lecture, but we can compare that result with what the modulus does. Okay, so if we run this program now, if we first build it, do that, and then we So what we'll do then is we'll enter the numbers. If we go back to our VHDL log file results, remember 8 and 5 were the last operands we were using, or combinations of sign for 8 and 5. And what we'll do is we'll see how does what we see here relate to what we see in our C++. So if we do -8 and -5 as dividend and divisor, the result from C++ is -3. So -8, -5 for mod, the result is -3 as it is for rem. So remember, those special cases we talked about, if the sign is the same, then mod behaves the same as rem. Okay, so we haven't learned everything we need to so far. That's unexpected result. So if we now go to different signs, so if we go to -8 and +5, now we're expecting the mod operator in VHDL to reveal a different value than it did for that result. So -8 +5 in VHDL, the answer is -3. So let's try that in C++. -8 and +5. And the result is -3. For remainder. Okay. For mod, it's not. Okay, so the VHDL mod is not the same thing as the % sign in C++. We can now conclude that. But it is the same thing as rem so far. So let's just, for sake of completeness, go and check the other combinations of 8 and 5 in terms of their sign. So if we go dividend of 8, divisor -5. The result we're getting is +3. So 8 and -5 for rem gives us the result of 3. For mod, it gives us the result -2 here. Okay, so clearly that reinforces our belief that the C++ to % is the same thing as the VHDL rem, which is not the same as the VHDL mod. And let's try the remaining one, +8, +5. We're expecting the VHDL rem and mod operators to be the same result, and we're expecting furthermore the C++ to give us the same result, which we're expecting to be +3. Okay, so 8, 5, results 3. Okay, so hopefully that's given you some insight into what the VHDL mod operator is, and now we understand it, we can find an application for it essentially. Okay, so if you're interested in these kinds of tricks and tips of the languages, then if you go to this link here, cadence.com/training, you'll see all the different kinds of languages and tools, training courses, and there's another example of the code. Okay, so I hope you found this interesting, and visit this website and you'll find on there contact details and the contents of the courses which may be of interest to you if you found this interesting. Thank you and goodbye.